Okay, so in this chapter, we're going to be looking at magnetic statics. Up until now, we've been looking at electrostatics, where we had static source charges that created electric fields. We're going to see that if we have a moving charge or a current, that's going to create a magnetic field. So we'll be looking at sources of magnetic fields in subsequent lectures, but right now we're going to look at magnetic force. So we know if you have a static charge, it experiences a force if it's in an electric field, which is equal to the static charge, Q, times the electric field it's in, E. Now, if we have a moving charge, it's going to experience a force in a magnetic field, which is equal to the charge times the velocity of the charge crossed with the magnetic field. So if you have a moving charge in the presence of both an electric and magnetic field, it experiences the following force called the Lorentz force, which is just adding up the force due to the electric field plus the force due to the magnetic field. So let's look at the motion of a moving electron in a magnetic field. And we're going to assume the electron travels at a speed v in a plane that's perpendicular to a constant magnetic field that I'll call B. So the force on the electron we get from the magnetic force, the electron has a minus charge, so we get minus E V cross, that should be B, not E. Let's see, I'll fix that right now. So the motion is going to be circular and in this case clockwise. So if we have the magnetic field going into the page, our electron, let's say at this point, is going towards the right. If we use the right hand rule, the thumb in the direction of the velocity, your index finger in the direction of the magnetic field, so going into the board, you get a force, your middle finger direction, which would be going up, but we have a minus sign because it's an electron, so we get a force pointing inward. You can do the same thing here to find that force, and so you get this circular motion. And in this case, with our magnetic field going into the page, it's clockwise. We can do the same thing for a positive charge. Again, let me change this to a B field. So now if we have a positive charge, we are also going to get circular motion, but now it's going to be counterclockwise in this case if we have the magnetic field going into the page. Here at this point, let's take this point, V, you put your thumb in the direction of V, you put your middle index finger in the direction of the magnetic field, so going into the page, and then you'll get a force pointing inward. So we'll get circular motion, and in this case, counterclockwise. So we can see that, or we know that whenever a particle is moving in a circular path, it has to have a force that's keeping it in that circular path. And that force is called the centripetal force. And in this case, our centripetal force is this magnetic force. So remember, the centripetal force is a force directed towards the center of the circle that is needed to keep a particle moving along a circular path. And this positive particle here is moving in a circular path because there's a magnetic force acting on it. So the magnitude of the centripetal force is mv squared over r, where v is the constant speed of your object and r is the radius of your orbit. The magnitude of the magnetic force in this case is qvb sine 90 because our magnetic field is 90 degrees from the plane in which our particle is moving. So you get qvb. So In this case, we know that our magnetic force is that centripetal force keeping our particle in a circular path, so we can set these two equal. The magnitude of the centripetal force, mv squared over r, and our magnetic force, qv times v. So the radius of orbit of the charge traveling in the magnetic field, if we solve for r here, it's going to be mv over qv. So the magnitude, this is the same slide, and we're going to call the frequency at which the particle revolves is called the cyclotron frequency, and we're going to call that qb over m. So what we find is that if you have a big magnetic field, your radius of orbit will be smaller. Okay, so you get a tight orbit. And if you have a smaller magnetic field, your r will be larger. And that, of course, is because of this inversely proportional r to b relationship that we found. So if your v has a component parallel to the magnetic field, then the particle will move in a helix. The parallel component of the velocity will not be affected, so it'll keep on going, in this case, in the x direction, but in the z-y plane, we get this circular motion. And this kind of corkscrew here is called helix motion. So we'll do this clicker question in class. Now we're going to look at the magnetic force on a current carrying wire. So a current is just a lot of moving charges, so we would therefore expect there to be a magnetic force on a current carrying wire. Current, as we know, is charge over time. And by convention, the current direction is that of a positive charge movement. So we can write current as charge over length times length over time, which gives us the charge density times the velocity of the particles. So lambda is the charge density of the moving charges, v is the speed of the moving charges. So the force on a current carrying wire is therefore just going to be adding up the force on all the individual particles in the current, and we integrate that, get the total force. So I can replace dq with lambda dl, and I can replace v, or what I did is v is in the same direction as dl, so I put dl cross b, and I have v lambda, and v lambda, so v and dl are in the same direction, and v lambda is just equal to I, our current. So we get the force on a current carrying wire is equal to I dl cross b. So you guys will be doing an example problem where you'll have to find the magnetic force on this segment of these segments of wires in a magnetic field. Now we're going to look at work and magnetic force. So let's see how much work does the magnetic force do on a straight wire of length 2r. So it's in a magnetic field B. This wire has a length 2r and a current going in this direction here to the right. You would have calculated in the previous problem that you get this upward force on the wire. So the force on the wire is 2RIB. This is what you calculated in example problem 5.1. And as the wire moves up, the charges in the wire are moving horizontally on the wire, along the wire, as well as vertically up a distance y. Okay, so our charges are now, they're still going to the right because this is the direction of the current, but now that we have this force moving it up, they're also moving vertically upward, let's say a distance y. So if we want to calculate the work, we have to be careful. It's not just going to be this F here times this distance y, and we'll explain why here. So the magnetic force is always perpendicular to the velocity and magnetic field. Okay, so if we are now, our particles in our wire, our charged particles in our wire are moving to the right because there's a current, but they're also moving up because of the force. The new velocity of our charges is in this tilted direction now. The magnetic force always has to be perpendicular to the velocity, so this is the direction of the force, the magnetic force. It's also going to be tilted. Okay, so we find that the magnetic force is tilted. The charge displacement is perpendicular to the magnetic force. Okay, so the charge displacement, right, our charges are going have a x component, but they're also moving vertically, y component. So we see the displacement of the charges in this tilted direction is perpendicular to the force, the magnetic force. So the magnetic force does no work on the charges because work is F dot D, okay, or F d cosine theta. Okay, our theta is 90, so the work done by the magnetic force on the charges has to be 0. So this is the case in any situation, so magnetic forces in general do no work. Okay. So if the magnetic force is not doing any work on the charged particles, who is doing the work? We see that the x component of the magnetic force opposes the current direction. Okay, so if we have resolved the magnetic force into a y component and an x component, okay, the x component is going in the negative x direction. Current of the current carrying wire, the particles want to go in the plus x direction. So the magnetic force is actually opposing the direction of the current, x component of the magnetic force. So let's find the x component of the magnetic force. If we do Q V cross B, and we do this determinant to find the cross product, V cross B, V has an x component and a y component, no z component. The magnetic field is in the minus z direction. So we get this for our force, our magnetic force. We see we have an x component and a y component. And so the x component is just minus q vy b. So it's going to be the battery or whatever voltage source that we're using that needs to oppose this force to keep the current moving. So the battery's force is QVY plus QVYB. And I can replace Q with lambda to R because that's the length of my wire and that's the charge density to get me back Q. So the work that's done by the battery is equal to the force that the battery has to apply times the distance that our charge go in a time dt vx dt. So we have the force of the battery, lambda to r vy, and then we have times b, and then we have our distance vx dt. And then I can rearrange the terms a little bit. So I get, if I multiply lambda plus vx, that just gives me my current, I. And then vy times dt, that's just the distance that my particles have traveled in a time dt. So the work done by the battery is I2RBY. So it's the battery that's doing the work, not the magnetic force. What the magnetic force is doing is redirecting the horizontal battery force into the vertical motion of the wire. Okay, so our battery's force is going this way, and the magnetic force redirects that so that we get some vertical motion. And this is an analogous to, for example, if you have a box on a ramp, the normal force is always going to be perpendicular to the surface, so there's not going to be any work done by the normal force. But if we push, let's say, the box with a horizontal force, that normal force is going to help redirect that horizontal force into vertical motion of the box in this case. So that's an analogy to what's happening here with our magnetic force and the force of our battery in this wire. So we can prove that magnetic forces in any case do no work. We do F dot dl, the work done by our magnetic force, if we just use the definition of work. If we plug in the magnetic force, QV cross B, and dl we can write as V dt. We know that V cross B is always going to be, that vector V cross B will always be perpendicular to our velocity vector. So if we get the magnitude here, or we do the dot product, this cosine theta, it's the angle between V cross B and V, which is 90 degrees. So we get the work done by our magnetic force is always going to be 0. Then we'll do a few clicker questions in class. And that is it for these lecture slides.